Welcome to Chemazon-Complete Chemistry. So in this video we are going to learn a very important concept in NMR spectroscopy that is called diamagnetic anisotropy. So these are some of the examples that we are going to see in this video. So in the last video of the chemical shift we had seen that an sp3 hybridized carbon, okay, the chemical shift is lowest, okay, it is 1.55, 1.5, 0.8. Okay, it is very less because we had seen that sp3 hybridized carbon, it has only 25% s character. And now if you see the sp hybridized carbon, which is more electronegative, why? Because it has 50% s character. The magnetic field experience will be more because it is more electronegative. So this carbon is more electronegative, so the chemical shift value will be higher. So it is seen that it is higher than as compared to sp3. Okay, so this is the order. sp it is 50% s character, sp2 it was 33% s character, and sp it is 25% s character. So now you would expect that a hydrogen attached to an sp2 hybridized carbon, the chemical shift value should be what? It should be between 0.8 to 2.4. okay, that is between sp3 and sp hybridized carbon atom. But if you see actually the actual chemical shift values, you can see they are much higher. Okay, 7, 5.3, 4.7, then 9. Okay, this is sp2 hybridized carbon. Here also alkene, this is sp2, and here also this is also sp2. So the question is why these chemical shifts values are higher. Okay, so for that the answer is nothing but diamagnetic anisotropy. So this concept we had seen in the last video, that the chemical shift of any proton, it depends on what? It depends on the magnetic field experienced by that particular nuclei. Okay, if the magnetic field is higher, the chemical shift value will also be higher. So let us first understand now what is the meaning of diamagnetic anisotropy. Okay, now what is the meaning of anisotropy? Anisotropy means any property that is different in different directions. Okay, this you might have also studied in solid state. There also you use this word that is called anisotropy. Anisotropy means property is different in different direction. Okay, anisotropic in Greek means different in different direction. So why this is called diamagnetic? Diamagnetic because there is something called as ring current. Okay, because of the ring current that we will see in the next slide what is the meaning of ring current. Okay, so basically in all the sp2 hybridized carbon we saw that there is what? There is presence of pi electron. Okay, pi electron cloud, they are very loosely bound, and because of this pi electron cloud there is something called as circulation of electrons. Okay, there is circulation of the pi electron cloud that generates something called as a ring current. Okay, so the molecule itself, molecule having pi electrons, they will have an induced magnetic field or magnetic field within the molecule that is called as bin or B induced. Okay, so this has some direction. So you can see this proton, it is directed like this. Okay, its magnetic field or induced magnetic field direction is like this. Now there is another magnetic field that comes into the picture that is called as B naught. B naught is the external magnetic field. Okay, that is due to the magnet. Okay, magnet present in the NMR instrument. So this direction is like this, and the direction of the induced magnetic field, both are in the same direction. Okay, so based on the direction of the induced magnetic field and the external magnetic field, the chemical shift value will be determined. Okay, now let us understand this with the help of examples. So the first example is benzene. Here you can see this purple. Purple is nothing but it indicates the electron cloud on the benzene ring. Okay, and if you see the direction of this proton induced magnetic field, that is same as that of the applied magnetic field. So the overall magnetic field experienced by this proton is much higher. Okay, so the magnetic field experienced by this proton is higher, so the chemical shift value will also be higher. Here you can see it is written induced magnetic field is in the same direction as that of the applied magnetic field. Okay, so that is why the chemical shift value of benzene this is higher, that is around 7 ppm. Similarly, for alkene, that is carbon-carbon double bond, and ketone, here also if you see the direction of the induced magnetic field, in both the cases it is same as that of the applied magnetic field. Okay, so what will happen? It will experience greater magnetic field, that is de-shielding will take place. Okay, de-shielding will take place and the chemical shift value will be higher. So what are the values? You can see it is 5, 4.7, and in case of aldehyde it is, in case of aldehyde proton it is 9 ppm. But there is another different example where you can see this is carbon-carbon triple bond, okay, alkyne. Now here if you see this proton of the alkyne, that is sp attached to an sp hybridized carbon, this proton if you see, okay, this is the direction of the ring current. So this falls inside the inside this ring current. So if you see the direction, external magnetic field direction is this, and this falls in this direction. You can see it is opposite. Okay, so the induced magnetic field direction is opposite. So what will happen? The overall magnetic field experienced by this proton is lower. Okay, so what will happen? The delta value will also be lower. You can see it is 2.4. It is lower than as compared to that of sp2 hybridized carbon. This is sp hybridized carbon. Okay, so these are some of the simple molecules, and there are some other molecules, special molecules like 18-annulene. Okay, 18-annulene, here if you see, how will be the ring current? The external magnetic field is like this, and how will be the ring current? Okay, ring current will be something like this. Okay, for this proton the direction is same. Okay, the black one, the direction is like this. But if you see the inner proton, the red ones, the direction is like this. Okay, it is, okay, red ones it is opposite. So that is why for the red one, black one, you can see it is de-shielded. Okay, because the direction is same, direction of induced magnetic field and the external magnetic field is same, so it undergoes de-shielding. The chemical shift value is higher. For the inner proton, okay, it undergoes shielding. It undergoes shielding, that is the direction is opposite, magnetic field experience is less, so chemical shift value is also less. Okay, such similar molecules is another molecule is paracyclophane. Here also you can see diamagnetic anisotropy. So this red ones, this is the external magnetic field. Again, if I draw the ring current, it would look something like this. Okay, the direction of the black one, that is this, and the benzene one, they are what? They are in the same direction as that of the external or applied magnetic field, whereas the red ones, the direction is opposite. Okay, so here also the red ones, you can see the chemical shift value is higher, whereas for that of the red ones, you can see it is in negative. Okay, minus 0.6. So this is shielding. Okay, and black ones undergo what? They undergo de-shielding. One more example, that is of, again here you can see, if I draw the ring current, it would be something like this. Okay, so the black one, again it is same as that of the external applied magnetic field B0. Here the B induced is same. Okay, for the black protons, that is why the chemical shift values, you can see they are higher. Okay, that is for the aromatic protons, around 7. Whereas the inner protons, that is the red ones, the direction is what? Direction is opposite. Okay, so in this way, you can determine the values of the chemical shift of these certain systems based on diamagnetic anisotropy. And last, we are going to solve this question. Okay, it is an MSQ type question, multiple select question. Which of the following is or are true about 18 annulenes? So we saw just now the structure of 18 annulenes. This is the 18 annulenes. First question, is it aromatic? So for aromatic, it should follow 4n+2 rule. So let us see how many electrons are present. 5 electrons, 2, 4, 6, 8, 10, 12, 14, 16 and 18. So if I put n is equal to 4, you can see I get the answer as 18. So it follows the Huckel's rule. It is cyclic, it is conjugated, and it follows Huckel's rule of aromatic. So it is aromatic. First answer is correct. Now second option, the inner proton resonate at 9.28, that is incorrect. The black one, that is the outer protons resonate at 9.28 ppm. So B is incorrect. Now there are 6 protons in the shielded region. So inner region we saw just now, the direction of the induced magnetic field is opposite. So they are shielded. Shielded means lower chemical shift. So this C option is correct. Last one, there are 18 protons in the deshielded region. Let us count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Okay, so there are 12 protons, okay, and not 18. So option D is also incorrect. So which are the correct answers? Correct answers are option A and C. So in this way, this type of molecules can be asked as an MSQ type question based on diamagnetic anisotropy. Okay, that's it for this video. I hope you have understood all these concepts. In the next video, we will see how spin splitting takes place, and we'll also see the splitting pattern, the normal ones like singlet, doublet, triplet, quartet, how it occurs, and the complex ones also like doublet of doublet, doublet of triplet, and so on. Thank you.